I will begin with a word of prayer. Heavenly Father, I thank you for this day. I thank you for these students. I pray that you help me to be able to communicate these things clearly despite my complete lack of preparation. I feel like a student praying for my tests. Amen. Sit here. Isn't that the quintessential prayer that's prayed? Dear Lord, please let me pass this test I have not studied for. Or, it's never quite that, but where were we? Very. Chapter 7?
Yeah.
Okay. And I think we just got to barycentric subdivision, is that right?
Yeah.
Okay, so, definition. If S is a simplex, let B upper S denote its barycenter. Sorry, I was thinking about the barycenter. So if K is a simplicial complex, what's that mean? What was a simplicial complex, guys? It was a collection of
simplexes and their faces.
So a bunch of simplices, but there's more to it, right? Had to meet those
faces
two
have to either
the two conditions.
be disjoint or intersect at one of the other cases.
Right. So. Okay. So. I was thinking, like, what if you illustrated that with a crowd of people? Like, they either have to not be touching, or they have to have their faces smashed together. Look, a simplex, not a simplex. I'm sorry, I didn't get no sleep last night. Let's see, a simplicial complex. Where was I? Define. Nathan's rethinking whether or not he should have asked me to do this today. SDK, the barycentric subdivision of K. How do we do this? How so? It's the simplicial complex. So many words. Why are there so many words in this book? With vert SDK equal to the set of barycenters where the barycenters of simplices where the simplices are taken from K. And with simplexes, BS naught, BS1, BSQ, what's Q? Where the S of I are simplexes in K with... What's that inequality mean?
It's the ordering, because we have the oriented simplex, right?
Oh.
At least I think that's what it is.
So these simplexes, do they don't have to be the same dimension, let's say, if that makes sense.
Right, yeah. It means that the vertices of one is a subset of the vertices of another.
Oh, okay. And then how do you decide which one goes first if they're disjoint?
Well, it doesn't have to be
I guess if they're disjoint,
linear order.
If you have disjoint simplexes, you don't get a simplex in the subdivision.
Oh, maybe I should draw this picture. Yeah, maybe draw this this picture will harm all ills, won't it? Wait a minute, no. It will heal all harm. No, wait, I don't know. I'm gonna give up now. Alright.
All ills? I mean, if ills are a bad thing, then harming them is a good thing.
Harming, let's see here, I don't
Is
know.
it though?
So this is B sigma. P2, what's this picture mean? P1, P naught, B naught, B1, B2. What are we looking at here? So sigma is P naught, P1, P2. What's that?
It's just a two simplex, right?
That's a two simplex.
I feel like this is a boring example
Oh.
of a simplicial complex.
And vert. So the vert. He says vert. SD sigma. It's just these 6 points, eh? So these zero faces, the barycenters, right? And then what's the last thing in there? B upper sigma is the
Very center of the
barycenter. Yeah, this is not going to help us with the inequality question we had, is it?
Yeah. Well, if you also included a different triangle that was disjoint,
Mm-hmm.
you wouldn't get any simplexes connecting some of the vertices of one with some of the vertices of another. I think that's what the inequality thing is saying. It's like the new simplexes will be like smaller, will be like kind of within a certain simplex, but not like between two different ones.
So if I have like a tetrahedron or something sitting over here, it's on its lonesome.
Right. And so you can subdivide that into 24 parts if you want. But like I'm saying that you won't get any simplexes connecting something from the tetrahedron with something from the triangle, I think.
Unless, of course, we build the tetrahedron as a cone over the triangle or whatever.
Yeah.
Or okay, examples of one simplexes in SD sigma are P naught V2, P naught V sigma. As an example of a two simplex in SD sigma, we have, let me color it. What's a two simplex? He says P naught B1 B sigma. P naught B1, so it's this guy. Right. Okay, sorry. Anyway, so definition. What's the definition next? If we have K as a simplicial complex, then what's the mesh of K? Mesh. I'm making a mask. I don't know what that would be. Mesh of K is the supremum over S in the simplex K and the diameter of S.
Yeah. So it's basically the same way we defined it in chapter 6, but with these simplexes not being functions.
So it literally is sort of the biggest size between. How's the diameter defined? I forget how diameter is defined.
It's the biggest distance between any of the points in the simplex.
Okay. So actually, if you actually made a grid that was this size, like mesh, the simplex would sort of slide through it. Because it could.
Yeah, it
Yeah.
could be
Kind of,
connected
if
in
you
weird
like,
ways.
Yeah.
If you like, yeah, if you twist it a little bit, I think.
I see. I'm not sure that's reasonable. That's good for a name for mesh. Anyway, okay, so moving along here. So then the theorem. Theorem 7.3. This is the simplicial approximation theorem. What's it say? If K and L are simplicial complexes, and F from the underlying set of K to the underlying set of L is continuous. Alright, then there exists an integer Q in the natural numbers and a simplicial happy Nathan simplicial approximation phi that goes from SDQ K to L. Simplicial, to F. So it's the approximation to F. Oh, goodness gracious. What's it now? Do we define that last time? What does it mean to be an approximation to the function?
37.
Oh yeah. So it's a simplicial approximation if for every vertex, the image of the function of
Image of
S.
the star of
Oh, the star. That's what it was. So the image of the star is a subset of the star of the image. So a star, if the star at P, the image of the star at P, is a subset of the star at the image of P under the simplicial approximation map. So it's kind of a funny. It's kind of a funny relation, right? So it's like F of the star at P, subset of the approximating map. The star, rather, of the approximating map. It's funny. All right, so what's his proof? He looks at the look at the vertices of L. Gives them a name. W sub J. Such that J is in some index set J. Right. And he says star. So the stars of the vertices, right, is an open cover. What is he, let be open cover?
It is an open cover.
Well, is an open cover, yeah. He's just reminding us the notation open cover of the underlying set of L. Since F is continuous, what's that say? F continuous implies that the inverse image of open sets are open, of course, right? And that is going to give us an open cover of what? see, F goes from where? From the underlying set of K, of the underlying set of K, right? Since K is compact metric, what? Oh, this is all Euclidean space, isn't it? Yeah. Yeah. Has Lebesgue number lambda greater than 0. By exercise 7.16, we can choose Q large enough so that the mesh of the, what's this silly thing called? The subdivision, that's right. So the mesh of the subdivision of K is less than 1/2 lambda. And it follows from exercise 7.15 that the diameter of the star at P is less than lambda for every P in the vertex of the standard division, the qth standard division of K. So what's this get us? We can argue that the diameter of the star at P is less than lambda for each P in the vertex of the subdivision, the qth subdivision of K, I suppose. And this is what? This is for the Lebesgue number lambda greater than 0. Alright, I'll just go in here. He says define sigma let's be phi, from the vertex of the qth subdivision K to the vertices of L, right, by phi of P equal to what? Phi of P equal to Wj.
Oh, hey, look. He actually uses the usual notation for defining the function here instead of using the mapping notation. This might be the first time he's done it.
Holy cow. You know, it's an interesting point. The point I can understand today. Thank you. Let's see here. Oh, I bet this marker works. We shall see. Where are we? So we got we're defining phi on where's phi going to be? Phi is supposed to be. Does that define? I mean, that's if you define it on the vertices. Oh, I guess I should keep going, huh? What is the WJ? Where WJ, I mean, which J, right? That's kind of like, where's, it's not entirely obvious yet. Where WJ is some vertex with star at P, right? A subset of the inverse image of the star of Wj. He says Wj exists by the definition of the Lebesgue number, and if there's more than one choice, just make a choice. Okay. So it follows that f of the star of P is a subset of the star of Wj. Every time I look back at this, I've completely lost my place. So annoying. Which is the star, is it equals? Yeah, oh yeah, actually this is actually equal to the star, oh, by definition, right, of phi of p. So we are done if we can show that phi is a simplicial map. I mean, he's only defined phi on the vertices, right? Phi eventually has to be defined on the qth subdivision of k, right? Is it enough to define it on the vertices
I think
of the qth subdivision?
Well,
so.
that gives
Okay.
you a affine map
Oh, okay.
on the entire simplex
All right.
for
Very
each
good.
of the simplexes, and so by extension, the
So-
entire complex.
So that makes sense. So the real question then is, if P naught through PM spans a simplex in SDK, does phi of P naught phi of PM span a simplex in L? He says exercise 7.8 gives us that the intersection of the stars is non-empty, so the empty set is not equal to f of the intersection of the stars. I'll write this down. Phi is not equal to f of the intersection of the stars pi, which by the way is a subset of the intersection of f of the stars at pi, which by the way is a subset of the intersection of the stars at phi of pi, I guess. So
the intersection of the stars of phi of pi is non-empty. And
Okay.
7.8 is an if and only if. So that means it spans a vertex. Or a simplex.
so yeah.
So 7.8 says that if the intersection of the stars is non-zero, if and only if that spans a simplex.
Ah, I see. Very good, very good. Then, let's see, up next we have corollary. What's our corollary? Corollary 7.4. If we have K and L simplicial complexes, and F mapped from the underlying space of K to the underlying space of L, I'm assuming continuous, then what? With a little bit more data here. K prime, a simplicial complex such that what? One, the underlying space of K prime is matching the underlying space of K. Two, still, this is data we're assuming, the vertices of K are a subset of the vertices of K prime. So I guess K prime is some kind of like, maybe you could say like as a refinement of K or something. So same underlying space, but you're adding more faces. And then the mesh, I love this, mesh of K prime is small. I feel like I'm in a differential equations course all of a sudden. Then, oh my gosh, he doesn't qualify it either. Then there exists, fine, whatever. There exists a simplicial approximation. Would you guys care to comment on what small means?
Maybe the author just
Smaller
felt.
than the-
Maybe he just felt like being Dr. Evil, just using quotations for no reason. Fire my laser.
It's like small enough for it to be like, for you to be able to make the same argument with like the Lebesgue number and whatnot.
Huh. I mean, there's nothing particularly. I don't see the small here either. Do you? What's
Well, I mean,
well,
if
the
you
mesh
think-
has to be less than lambda, or
oh,
lambda over 2.
okay. So the small probably means that the mesh has to be smaller than that lambda. How could that be? I mean, how can that? I'm sorry. How is it possible for that not to happen if the vert k is a subset of vert k prime? Doesn't that imply smallness? I mean,
It doesn't. I mean, like, if you have like all the if like all the extra vertices are like closer to it, closer to like one point, and still far away from another one, it doesn't really decrease the mesh that much. I don't think.
I think
but how could it? I guess my question is, how could it possibly increase it?
Would increase what?
The mesh.
I don't think it will.
So why is 3 necessary?
I mean, they're just.
Because we
making
don't
that
know
point.
what the mesh of K is. Like, that's not really important. In the proof of 7.3, we look at the mesh of the subdivision, which we can make arbitrarily small.
Ah. Okay. Definition: a subcomplex. Do you have something to add, Nathan? Or?
No.
Okay. A subcomplex of L is a simplicial complex K. Sorry, words. A subcomplex L of a simplicial complex K is a simplicial complex contained in K, with the vertices of L being a subset of the vertices of K. Yeah. I think I might have guessed that. Note that the subdivision K is not a complex. It's not a subcomplex of K, nor is K a subcomplex of the standard division K. Okay. For any Q larger than -1, the Q skeleton of K, denoted by K parentheses upper Q, is the subcomplex of K consisting of all simplices S and K with dimension less than or equal to Q. So like if your simplex was the tetrahedron, could you look at like the one skeleton, and would it just be like the vertices of the tetrahedron and the edges, but not the faces? Theorem 7.5. If M is less than N, then every continuous map F from Sm to Sn is null homotopic. What? You know, all of a sudden. It's like simplicity. Sphere? What? Sphere? Let's talk about sphere. Didn't we already calculate everything for spheres anyway? Here's this theorem. I'm just talking. Theorem 7.5. If M is less than N, then every continuous map F from Sm to Sn is null homotopic. Okay, so what's the argument here? He says let K be the M skeleton of an M+1 simplex. and let L be the n skeleton of an n plus 1 simplex. Oh. If we regard a f a continuous map from K to L. F a continuous map. Now what can we do that? If we have a continuous map from the M sphere, how does, I mean, where are the simplices entering into the sphere here?
It's 4 o'clock.
I think
PM.
they're implicitly using the fact that SM is isomorphic to the M skeleton of an M plus 1 simplex. They're just not stating that.
Ah. Let's see
Because
here.
why would you state it? It's all the exercise left to the reader.
So for example, the skeleton of just the triangle
It's gonna be that.
is just the edges,
Right.
And the vertices.
and that's
The circle.
the circle. Okay. Or the tetrahedron's
Faces.
faces, just the sphere. Yeah. Okay. Okay, I think that's actually reasonable. So we can regard this as F as a continuous map. Anyway, there's obviously a way to get from that map to this map. Anyway, right? I mean, passing through the appropriate homeomorphisms. And then he says let phi from the qth standard subdivision rather, of K to L be the simplicial approximation, right, to F. Then what do we get? Since the dimension of SDQK is equal to the dimension of K is equal to M, and we can work an exercise to show that the image, what's that bar on phi mean? The image of bar phi,
With the induced map.
the induced map, subset, induced in what sense? Oh, subset of.
The functor maps the
Oh.
complex to the underlying space.
Okay. So the image of the induced map is a subset of the, and that was the M skeleton of the underlying space of the N's. The underlying space of the M skeleton of L. And so phi is not surjective. Why is that? Oh, because, well, why is that? We're assuming what? M is less than N, right? So the underlying space L here is n-dimensional, right? Or it's an n skeleton. I don't know. Is that an n skeleton n-dimensional?
Yeah, because it contains all simplices dimension less than or equal to that number.
Oh, okay. Why is it that the induced map of phi is not surjective? Image of this seems to be the culprit here. The image of the induced map of phi is a subset of the. Oh,
Well, because it's some map to, that's what we're using for.
so that has dimension. I mean, that means this has dimension at most M. But
It would have to be n.
that has dimension n, so it can't hit all of L. Is that right? I keep talking myself out of it. I'm sorry, guys.
Hmm. Well, phi is a map from the qth barycentric subdivision of K to L. So if you look at the induced map under the functor, that's a map from the induced spaces, right? Then the induced space of the mth skeleton of L is a subset of the induced space of L. So this says that the image of the induced map of phi is a subset of the induced space of L,
So this
which means that the
this is a so that you're, I could do this is what you're saying.
right.
Yeah. And that's not
The second one's definitely not.
a strict right containment. So that means phi is not surjective, right? Okay, so phi is not surjective, hence the image of the induced map is a subset of L, the image, the underlying set of L with a point removed. What? This follows that?
So if it's a proper subset, then there's at least one point that's not in it. So it's definitely a subset of L minus that point.
Oh,
And
which
that's
is
what we need for it to be contractible. Like L minus a point is contractible.
and so so the induced map of phi is null homotopic.
Huh.
So this is contractible, and that implies that the induced map of phi is null homotopic, which then implies that F is null homotopic. Corollary: if n is greater than or equal to 2, Sn is simply connected. He says, what does he say here? The theorem shows that every continuous map from S1 to Sn is null homotopic.
Because 1 is less than n.
Ah.
What is theorem 1.6?
That's cool. So of course a mapping, I mean that's what is
Oh, well, that's basically the definition of simply connected. Pretty much.
right, I mean you look at I mean intuitively speaking, simple connectedness has to do with
Paths.
paths deforming specifically loops deforming to points, not getting stuck on things, which we capture more formally in terms of the null homotopy of the map. And but then by that theorem, the theorem above, certainly 1 is less than 1 is less than n if n is greater than 2. Circle is really special, isn't it? Yeah. We've already sketched proof of this corollary in exercises 3.20 and 3.21. The result does not follow, however, from the Hurwitz theorem and the fact that the first homology of Sn is 0 for n greater than or equal to 2. One can conclude from these data only that the fundamental group of S, and 1 is its own commutator subgroup, and such groups do exist. Every non-abelian simple group is such a group. Oh, so he's saying that the earlier the earlier thing he sketched is a plausibility argument, but it's not ironclad because there are counterfactual groups. No. Other, yeah. Let us mention a famous problem. The Poincare conjecture asks whether a simply connected compact N manifold having the same homology groups as Sn is homeomorphic to Sn. It's not too difficult to show that the conjecture is true when n equals 2. For n greater than or equal to 5, the conjecture was solved affirmatively by Small in the 1960s. The case for n equals to 4 was solved affirmatively in the 1980s by Friedman, and the familiar dimension 3 is thus the only open case. Wow. That has been solved, I believe, since this book was published. That was solved about the same time as I was in grad school. I think that's, is it Perlman?
Yeah.
Yeah. One of the more interesting mathematicians of our time.
We figured it out, then became a hermit.
Alright, let me take a look ahead here for just a minute. Whoa. There's a rather impressive German word later in this chapter. I was distracted by it. Alright.
Where is that?
Oh, Hever.
Oh, here it is.
You found it.
Hauptvermutung. I don't know how to pronounce it.
Hauptvermutung. Anyway, principal conjecture. Alright, let me read here for a little. Abstract simplicial complexes. We're going to define homology groups of a simplicial complex K, which turned out to be isomorphic to the homology groups, this is parenthetical comment, which will turn out to be isomorphic to the homology groups of the space X equals to the underlying space of K, as defined in Chapter 4. This construction works in a simpler setting, which we now describe. So this is a rehashing of things that have been done before for the singular complex. Now he's redoing them for. So basically, I think we're removing the extra packaging of the thing, the continuous map part, right? Is that fair? Not sure what's going on here. He seems to be saying this construction works in a simpler setting, which we now describe. What was Chapter 4? Chapter 4 was what? Singular homology. So I think we've done these before for the singular homology, some of it. Anyway, I will get to it. A V be a finite set. An abstract simplicial complex K is a family of non-empty subsets V called simplexes such that if V is an element of V, then the set containing V is an element of the complex. If S is an element of K and S prime is a subset of S, then S prime is an element of the complex. So basically, if you got a face, you got all the subfaces, right? And if there's a point in the finite set, then that has to be included as a zero face, if you will, in the complex. Okay. So an abstract simplicial complex K is a family of non-empty subsets V called simplexes such that these two conditions are met. One calls V the vertex set of K and denotes it by vert K. A simplex S and K having Q plus 1 distinct vertices is called a Q simplex. For example, if you have two distinct vertices, you have a 1 simplex. 3 distinct vertices gives you a 2 simplex. This is my happy place. I should be writing these things. I'm going to keep reading though because I think we understand. If K and L are abstract simplicial complexes, then a simplicial map phi from K to L is a function which maps the vertices of K to the vertices of L such that whenever you've got a simplex in K, then the set of images is also a simplex in L. There could be repetitions in the latter list, so you could have your simplicial map doesn't have to be injective, you know. Theorem 7.7, all abstract simplicial complexes and simplicial maps determine a category denoted by
Bold script K, upper A.
we'll go with that. Proof by Nathan. Alright, equivalences in a category. I'm using proof by Nathan. It's a new method of proof. Equivalences in the category bold script K with an upper A, and in the category bold script K without the upper A are called isomorphisms. That doesn't... Okay. Yay. Alright. Fine. Every simplicial complex K determines an abstract simplicial complex K upper A with the same vertex set. Let each simplex S in K determine its vertex set. Vert S is a subset of vert K.
So, yeah. So regular simplicial complexes are just a specific case of the abstract.
Hopefully he's going to give us a more abstract example, so we don't feel like we're just... Let X be a topological... Please, let this be an abstract example. Let X be a topological space, and U a finite open cover of X. Alright? Define an abstract simplicial complex having vertices the open sets in U. Ooh! The vertices are the open sets in U. That's weird. That's really weird.
This reminds me of hypergraphs.
Oh, it does not me. Then again, I understood the hypergraph, so that's probably part of it. Nathan's like, I hate you. Sorry, I shouldn't tease Nathan when he's sick. It's not right. Where was I? We declare that the open sets U0, U1, UQ, and U form a simplex if their intersection is non-empty. This simplicial complex is called the nerve of the open cover U, and it's denoted by NU. Ooh, that's a fascinating name for this. I think it's just a fantastic name. Like when they say that, I feel like I can almost see what they're talking about now. Like, That's actually very cool. Well, Well, maybe not. I was thinking about... Well... Does this meet the conditions of an abstract simplicial complex? If V is in V, then the set containing V is subset of the complex. Well...
Yeah, I think the intersection is not empty there.
Yep. And if S is in K, then S prime is a subset of... So if you have a subset of subcollection of the open sets whose intersection is then empty.
The intersection is going to be not empty.
Yeah. Next, man, that's interesting. Let G be a finite group. Define an abstract simplicial complex, QPG, whose vertex set consists of all non-trivial P subgroups of some fixed prime divisor P of the order of G. All non-trivial P subgroups, eh?
Okay, thank you.
Oh, and also, okay, so how do you define a simplex? Well, the subgroups P0, P1, PQ form a simplex if their intersection is not the identity. They didn't tell. Did they tell us what the? They didn't tell us what the simplicial complex was here, did they? I guess we're just supposed
it's
to.
made up of all the simplexities.
I guess we're just supposed to assume the simplicial complex is specifically constructed as to meet part 1 of the definition. Yeah. Example 711. If K is an abstract simplicial complex, we construct its barycentric subdivision, SDK. Here, SDK is also an abstract simplicial complex. We define the vert of SDK to be simplexes, sigma, such as sigmas in K. We define a simplex in SDK to be the set, sigma 1, sigma not, sigma 1, sigma Q. Oh, and there you go, there's the meaning of the order. Sigma less than sigma prime means that sigma is a proper subset of sigma prime, right? What is this all leading to? The construction K to Ka in the example 7.8 defines a functor from boldface K to boldface K with A. The next theorem says there's a good way to reverse this procedure, obtaining a simplicial complex from an abstract one. Oh. There is a functor. U. Oh, fine. It's easier to write it than to say it. It's a point you have to admit defeat, you know? Theorem. There exists functor U from K to K such that K what manner of morphism am I talking about here? Is this homotopic?
In terms of the isomorphism.
Is this isomorphism? Is it
Yeah, I think it's isomorphism.
K is isomorphic to U of Ka for
I
all
defined it here.
Or what is
K in the objects. Okay. And L is whatever morphic to U L A for every L in the objects of Ka.
I think this is probably a categorical equivalence. If those are natural isomorphisms. Which makes a lot of sense.
I saw a section called calculations. Stoked about that. Next time we cover, I am going to go to that calculation section and do it. I'm tired. Sorry.
How far ahead is it? Is it after
But
the
I think there's a soul searching. There's about 5 pages between that, maybe more.
Oh yeah,
And-
it's right after the Hauptvermutung.
Yeah, I think I might. Well, I don't know. I should probably read it and then decide. But it seems like a lot of what's between where we are and where's there. It's just like, here's how this compares to singular. It's entitled "Comparison with Singular Homology." I'll have to read it and decide what I should say. It's okay. Anyway, going on here. So this is a theorem. The proof. He says let L be an abstract simplicial complex, V the vertices of L, V naught, V1, Vn. The standard simplex, delta n, has vertices, standard basis, right? E naught through En. If S is equal to V sub I naught sub IQ is a Q simplex in L, define the, let's see here, what do you want to call that? The induced, is it the underlying set? It's the corresponding simplex to S?
Yeah.
To be, it's just the, I see. So it's the corresponding standard simplex. Just, it's almost like it's just like linear algebra, right? I mean, it's like he's trading the abstract basis for the standard basis, right? So he's trading a abstract Q simplex for a standard Q simplex, I suppose. Finally, define UL as a family of all such corresponding simplices for S and L. It's plain that U of L is a simplicial complex. Indeed, U of L is a subcomplex of the standard N simplex. It's easy to see the simplicial map phi from L to L prime in Ka, which is a certain parenthetical comment, which is a certain function from vert L to vert L prime, corresponds to the obvious simplicial map U of phi. Wait a minute. Is this a parenthetical comment within a parenthetical comment for a second? Oh no, it's, for a second there I thought we'd gone 2 levels deep. It's okay, I think we may never wake up from the proof. I pinched myself and then I was still proving things. I don't know how deep I've gone. Sorry. A surprisingly good movie despite the presence of that horrible actor. Sorry, I digress.
Which one?
I don't know why I dislike him, but I just have something about it. You know what it is? Is my sister-in-law's sister got so obsessed with Leonardo DiCaprio after Titanic. She used to go around, Jack. Just... You guys did not suffer that movie as I suffered it. Anyway, I go on. Anyway, getting past the parenthetical comments, one quickly verifies that U from boldface K with an upper A to K is a functor, and the isomorph. So anyway,